Fabiana has been leading data science teams in multinationals and startups across the board. Oh, she has an academic background in applied maths and a master's in data management, combined with other degrees in deep learning, security, and private AI. But these days she focuses on YData as a co-founder and CDO. She combines data understanding, causalities, and privacy as her main field of work and research. Her mission is to make the data actionable for organizations across the globe. We're so excited to have you here, Fabiana. Let's get you on the screen so we can get our hands on the keyboard and start the show. So I'm gonna now bring you on. Fabiana, what is up?
Hello. Great intro. I've never had one of this before. No.
Nice.
I saw on the other episodes, but I guess I was not expecting to be so good. It sounded really well, my bio.
Yeah, I feel like you wrote it in iambic pentameter or something. So anyway, we have successfully completed the first phase of this meetup. Let's jump into the second one, and I'm gonna give it all over to you, Fabiana. And yeah, maybe do you want to share your screen? Let's see if this can work and make sure that it all goes according to plan. Otherwise, Ben and I can jump back on here. And there we go.
Okay.
Cool. So I'll sign off. I'll leave it up to you. And we'll jump in and ask questions if we need to.
Okay, awesome. So, as promised, today we are going to type in, or at least dive in to the developing, let's say, a solution or a pipeline for what we call synthetic data generation. So, in a nutshell, we are going to combine three main open source solutions that you can find related with within the data space. We have the YData synthetic, which is the package that is responsible for the generation of synthetic data while leveraging generative or depict generative architectures, more specifically GANs. Then we have the pandas profiling, which is what I like to call the one line of code exploratory data analysis that will provide us some very useful insights for us to keep our synthetic data within our expectations. And last but not the least, the Great Expectations package, which a lot of you might already know as well. And it's an impeccable tool for doing great data engineering, but not only, as we will see today, can also be widely useful if you are testing, validating, and trying to generate synthetic data with what we call quality in terms of fidelity and utility. So I promise not to bother you with too much of the the let's say more boring stuff about synthetic data or the scientifics behind it. But if by any chance you feel like you would like to understand better why there was a couple of decisions that I've made or I've exemplified here, just drop a message or so. I'll be happy to explore and detail more on the specifics. Right. So jumping right into the code and what we are going to build here today, I have to emphasize two important things. So one, if because the packages ends up using different versions of NumPy and Pandas, it is important that we keep two virtual environments separated and we create two different kernels for different purposes. In this case, we will need a specific Conda environment, or at least I do recommend using Conda as it was what I've used. One Conda environment with Python 3.8 for pandas profiling and Great Expectations, both together, as they are. We are going to run them together within the same notebook, and one environment specifically and particularly only for YData synthetic or for the step of synthetic data generation. We will use the profiling kernel, as I call it, which includes pandas profiling and Great Expectations, for both the first notebook and the third notebook. And regarding the synthetic data generation, we will be using what I call the synthetic kernel, which only includes YData synthetic. All the code that I'm showing here, or the notebooks that I'm showing here, you can easily find them at our open source GitHub repository. If you just go to YData synthetic, under integrations, you can see expectations to synthetic data, and that's the scope that we are going to cover today. So yeah, let me jump right into this. And if you do have any questions, and before I do forget, if you are leveraging a GPU machine, which is highly recommended to train the model for synthetic data generation, don't forget to set up correctly your TensorFlow environment. Otherwise, your CUDA drivers your GPU might not be correctly identified by the TensorFlow engine because you do not have the right CUDA drivers installed. We do have a very easy to use setup file, and you can find that setup file here at a set of utils called Conda TensorFlow GPU. If you do not have GPU, if your GPU is not powerful enough for these processes, don't bother. It will still run on CPU. The only thing it will be, the only impact it will be highly time consuming, and that's the only difference. Let's jump into this. Specifically, let me just change here. Yeah, so for the use case, I've decided to use a very simple and easy to use data set from Cargill, so the cardiovascular disease. I'm not sure if Dimitrios, I can leave the link for the data set on the stream, or how do you prefer to do it?
Yeah, just throw it in the chat and then I'll put it in the stream.
Okay, perfect. So yeah, thank you. Just dropped that. So in a nutshell, you can also find the dataset in our GitHub repo, but you might find it easier to use directly the download from Kaggle if you don't want to use the folders of our open source project. It is under cardio sample, as we can see here. So maybe, is there any questions so far?
Nope, so. Nothing yet.
Yeah. Okay. Okay, so the first step is it's pretty straightforward. So we are going to leverage pandas to read the data set into our notebook, and as pandas profiling indicates, and we are going to right away leverage pandas profiling. So as it is, as by the naming of the package, we can easily understand that it generates profiles out of pandas data frames. So specifically, the integration is designed to work with pandas data frame. That's why I'm also using pandas to read. In case of using bigger data sets, the story can be different. But specifically for the cardiovascular, which is a data set that fits into memory, I'm using straightforward pandas to read it. The tool, as I mentioned, is it's a kind of a standardized exploratory data analysis for data scientists to explore both in a univariate and multivariate perspective. As you can imagine, the more data or the bigger the data set and the more columns the data set has, the exploratory data analysis tends to become more complicated and time consuming. And pandas profiling is a way to not only standardize, but also make this a commodity. For you to run a full profiling and a full exploratory data analysis is as simple as just calling a profile report on the data, give it a title, and then exporting to a notebook iframe. So export the HTML as an iframe. In a nutshell, this HTML represents already the exploration of your data. So let me just run this. So as you can see, I'm here. I just created my profile. I'm running my iframe. Then it is summarizing my data set, is extracting minimums, maximums, visualizations, building the histograms, and all of that. One of my preferred sections ends up being the warnings. So it just tells us a bit what might be concerning, or we might need to drill down a bit further. In this case, my only concern with this data set is the presence of duplicate rows. And bear this in mind, as this will be important also when you are assessing your synthetic data. As you can imagine, the presence of duplicates at the level of the original data set does have an impact while you are generating synthetic data. And that's why also the profiling ends up being so relevant. But don't worry, I'll be covering this while in the process of synthetic data generation. So very straightforward. There's nothing too complex about this. It's just really extracting all the details about your data. But you think that, well, given that I have here a pretty good exploration about my data, wouldn't it be nice if in a flow of data engineering, or even in the flow we are considering today, synthetic data generation, that I could just from these minimums, maximums, and other behaviors within our data, we could just generate a couple of rules or constraints or expectations of what we might want to see from other data sets that theoretically should be derived from this one as a result, or a new flow of inflow of data, or even if you just generate data from the synthetic data from any original data set, that would be nice. So instead of having to manually set those rules, what pandas profiling and great expectations allow you to do is to, in a nutshell, generate what we call an expectation suite, an automated expectation suite, right from your profiling. In this case, I have chosen to generate a smaller profiling. This because I'm not going to generate any expectations out of the multivariate validations like the interactions or the correlations. So I just I decided to generate a new profile report, setting my explorative as true, and this will generate me a report only focused on the univariate validations, such as the histograms, the calculated max, minimum standard deviations, and so on. Afterwards, I do need, and in case you haven't yet used in this folder any Great Expectations project, you need to git init or to Great Expectations init your folder. Okay, so this will, in a nutshell, create a folder with the details of your Great Expectation context for this project. That's very important for you to do at your terminal. I won't be replicating here because I do have mine already initiated, but that's important prior running any one of these lines. If you don't do this, anyways, the package, the Great Expectation package, will alert you that you need to do it. So
So I'm actually really excited about the synthetic data generation section of this because I work a lot in the NLP space. I don't work a lot in the imaging space. So I'm pretty excited to see how it can be used or in tabular, but synthetic data generation, at least where I'm working, isn't particularly popular. So I don't get to work with it that often.
Nice. All right. And anybody else that is here with us, let us know what you're excited about. And I'm going to hand it over to Fabiana again. Hopefully Gonzalo he'll be a little more quiet now.
Hopefully he has toned down his voice. Let me know again if you pick up anything else. And sorry for that. But yeah, I'll be jumping into the cool stuff in a couple of minutes. But definitely, let's just wrap it up the area of, okay, how can we go from a simple exploratory data analysis all the way towards extracting a couple of expectations that we can apply further down the flow of our pipeline. Okay, so in a nutshell, I'm running the profile. I'm sending it. I'm also storing it to a JSON file, so I can reuse at the moment of my synthetic data generation. I'll be explaining why, but in a nutshell, profiling kind of is crucial at every single step of the data science project. And synthetic data generation ends up not being an exception for that. So just storing my JSON profile, I'm going to create my data context at the level of this notebook and export and create a suite of expectations right from my profiling. So it's very simple. I just use the same profiling I have created earlier, and I do select the method to expectation suite. Afterwards, and because I'm not interested in seeing the data docs, meaning the validations that were done on top of the data right away, because I'm just only interested in the generation of the suite of expectations, I'm going to set the build data docs to false along with the safe suite and run validation, as I don't want to do that right away. Afterwards, well, I told you that it would warn if I don't have a Great Expectations environment created. Let me just open a terminal here so I can run this. Okay, and I don't want to create any. Okay, that's done, and I just created my data docs, but in a nutshell. So okay, everything is set. Now I have to restart my kernel, and it will do the job. So after we successfully create our suit of expectations, it will be, let me see if I created the, yes, I created the expectations on the wrong environment. Sorry. Um, yeah. Sorry, I forgot to create it in on the, I don't want to configure any data source, so all good. Yes, now it's good. I do have my great expectations context already created here, so it will probably work now. Okay, yes, it worked, it ran. So I do have my expectation suit already here. It's already created. I can show you. As you can see the name I gave, the Great Expectations version I'm using to generate this suit, and all the expectations that were automatically generated per column. After that, I want to then save my expectation given a data context that I have created. Just run this line, and afterwards, if I want to run the expectation suit, I'll be showing on the other notebook, so I won't be running these 2 lines of code as I don't need them as of now. Just to summarize, this was just the initial exploratory data analysis, just for us to have a sneak peek at the data, plus the generation of what we consider the automated expectations, so we can further down the process use those expectations to assess the quality of our synthetic data, in particular from a fidelity perspective. With no further ado, let's jump into the synthetic data generation, which is probably what you are most excited about. In a nutshell, as I mentioned, and just to recap, I've changed my kernel to use my Conda environment where I only have installed YData synthetic version 0.8.0. As a first step, I'm both going to read my dataset, my original dataset, and my JSON profile, which the pandas profiling I stored as a JSON, because I will be needing some of the let's say the inferences from the profiling to feed into the synthetic data generator. In this case, I have both. You can see the JSON profile very quickly here. So as you can see, pretty detailed. We don't need this cell for now. It was just for you to see that everything that you see here in this kind of HTML file, you can very easily export it as numbers as well for you to reuse in your flows. So if you are building a pipeline, you can still use pandas profiling for a lot of your validations, because you can export everything as a number for your consumption, or as a value in a JSON file. So it's very useful, especially if you are building an automated flow of data, for instance, and you are not into visualizing your exploratory data analysis that much. You are more into automating some validations, some warnings, for example, like we had the warning section. So that's why here the export to JSON kind of is so useful and important to mention. So the synthetic data generation itself is no exception for that. One of the things that pandas profiling infers automatically is the variables that are categorical and the variables which are numerical. And that's exactly what I'm running in this cell. So I'm using the automated inference of the JSON in terms of the variables, and I'm extracting the variable type that was identified. So the ones that were selected as numeric, I'm keeping it in a numerical columns kind of list, and the ones that are categoricals, I'm keeping it in a separate list. This is highly important for the process or to feed into our synthetic data generation. Why? Different types of data, and specifically the most standard ones that we usually are explore at the level of of data science, which are numerical variables and categorical variables. They do have different needs of encodings and preparation. This step ends up being crucial exactly for your model or your synthetic data generator to be able to identify which encoding to apply to each one of the columns. That's why this is so crucial and important. This has a high impact on the quality of the data that you generate because different choices at the level of the preprocessing end up resulting in different levels of quality for your data. Particularly, and on the synthetic data generation side, and you might be wondering why I'm not considering this column. This is highly related with the architecture I've decided to explore with you today, which is what we call a conditional GAN or a conditional generative adversarial network. A conditional GAN architecture kinds of assumes that all the process of both training the GAN and generating the data from the GAN generator is conditioned to certain values. The conditions usually can be used are one of the columns of the data set, particularly when you are dealing with imbalanced data sets. It's highly recommended that the imbalanced variables are the ones used as conditions for the generation. This helps you to avoid what is called the mode collapse, which means that if you have imbalanced variables, the GAN will have a hard time understanding that, in capturing the modes and the distribution for the data set that is underrepresented, which means that in the end we'll be generating more variables of the most represented class. So conditional GANs are a very effective way of dealing with that and ensuring that you keep the balance or you keep the original representation of your data in terms of classes, but also can be highly useful if you are trying to balancing out a data set, for instance. Let's say that you have, it's not the case of cardiovascular disease data set, which I can show you very quickly. I've selected the target variable as cardio, so it's the variable that someone is trying to use for a machine learning model. The variable is, it's pretty balanced. And if we do an analysis of gender per cardiovascular disease, we can also check that gender, it's pretty balanced, which means that this data set is very well behaved. So you don't really have to worry with using a conditional and for those cases. But if you have those, you do ensure a more quality in the end anyways. But I'm talking about here GANs and mode collapse. But I'll just give you a brief example of a brief explanation of what a GAN architecture can be. So, in a nutshell, every generative adversarial network can be composed by at least two networks that are competing with each other: the generator and the discriminator. The generator is responsible to receive what we call a noise vector and to generate fake records out of that noise that it receives. With the more epochs you train, so the more epochs the generator, the more data, original data the generator sees, it is expected that the generator gets better at tricking what we call the discriminator, which is none other than a network or a model that is labeling the records that receives as fake or real. So theoretically, the more the generator it trains, the better it gets at tricking the discriminator, because the generator does receive the loss of the discriminator, and the more epochs it passes, also the discriminator theoretically gets better in distinguishing between what is real and fake. So it's a balance between this min and max game, as we call it, in order to achieve what we call the generation of good quality synthetic data. Of course, this is the most simple version of what we call generative adversarial networks. There are a lot of flavors. Some of the flavors are related with generating different types of data. For instance, if you want to generate what we call sequential data or time series data specifically, you most probably will try to leverage a different flavor of GANs, where you might include two generators, for instance, one discriminator, or even one generator and two discriminators, where one discriminator is setting as fake or real for the events, and the other one is just setting as fake or real for, let's say, the average on a long window. So one uses a Windows just, and the other one, and the other discriminator ends up using a combination of windows, for instance. So it's a way of ensuring the short and the long sequence. So in a nutshell, what I want to say is GANs can get as complex as you want, but bear in mind that the more complex they get, also the more complicated it gets to train them. They are very time consuming, and besides that, it gets very tricky to optimize. So if a regular machine learning model, it's already interesting enough to optimize, but there are solutions to make it possible. Imagine an architecture like this, where you have the same amount of parameters times the amount of models or generators and discriminators that you consider. It's a complete nightmare, and that's what makes the adoption of GAN so specifically for production very challenging, but possible, bear with me, but with a lot of tips and tricks associated in order for you to be successful. Some of those tips and tricks are mostly related with the loss functions that you end up using. In this case, for this particular use case, I'm using what we called Wasserstein conditional GAN with gradient penalty, which means that I'm using Wasserstein loss, which ensures more stability for the training of of my GAN, so it does not fluctuate so much during the training with the gradient penalty applied. And as I mentioned earlier, condition to the target variable, which is in this case the cardio column. With no further ado, I'm just showing the code for this particular example. Bear with me. I'm not going to run again for the amount of epochs it should be running in order to achieve results. But I can give you a brief overview on the hyperparameters that you should consider at least. So one of the hyperparameters is the noise dimension, meaning the size of this vector that you send for the generator. It is just, it can be as big as you want or as small as you want. To be completely fair, it's not the parameter that impacts the most the quality of your training. So I'll just cover the ones that have the majority of the impact. Batch size is one of them, for instance. So theoretically, the bigger the batch size, the better you will get at training. But there's also a problem. So the generator will get too overfitted and too fast very good at tricking the discriminator. This will kind of put your the whole concept behind GANs will not be beneficial, because in the end, your synthetic data will just be overfitted to the real one, which means it will be just like the real one, equal. So there is a kind of trade-off that you have to consider. So neither too small, neither too big, but big enough for you to ensure a proper training. In overall, for smaller data sets, such as the one I'm using, 64 works for the majority of the data sets. If going for a bigger, try to double or even to triple this number, and probably it will work out. But what I'm telling you is that the batch size, or the decision behind batch size, will depend a lot on the size of your input data set combined with the number of columns that you have available. So bear that in mind when setting this hyperparameter. These ones I have extracted from literature. Usually the recommendations are to use 0.5 and 0.9. They don't vary that much. So it's probably something you don't need to worry so much. About the epochs, this is where it also gets important for you to set them really well. So the epochs are the ones that might be the difference between having a GAN that have successfully converged, which means that successfully learn from your data, or having a GAN that it's worthless. Meaning, if it trains too little, it won't learn the data. If it trains too much, the patterns can also can also break. So again, this depends a lot on your choice of batch size, and because the batch size will influence the number of iterations per epoch, and that will decide on what is best for your data set. Specifically for this type of data sets that are around the size of cardio, 500 epochs minimum usually lead to good results. One fun fact, or not so fun fact, about GANs is that the fact that you might be thinking, oh, how can I hyperparameter tune this? Would be also so helpful to have an hyperparameter tuning done at this point. It's not that easy. It's not as straightforward as you think, and it's an open question at the level of the research. So the tuning will depend. Let me just. Something is happening here. No, all right. So the tuning.
Just a random one that we just got in the questions. Why 500 plus 1? Is there any particular reason regarding epochs?
There is in particular, it's not related with the epochs themselves, but it's a good question. It's more related with the visualizations, and when I'm using visualization, I want to visualize what happened at the 500 epoch. So for that reason, I just added one in order to store the 500 epoch, let's say. So it's just let's say a support for the development,
Nice.
not a scientific reason about that. And yeah, for some reason, my my environment is not okay, but I'll just move forward. Anyways, I've run this previously, so just for the purpose of demonstration. About the learning rates, this is where it also gets important. So I would say that when considering GANs for synthetic data generation, you have to consider at least 3 parameters as the most important ones for you, at least 3. So batch size, epochs, and learning rate. Those are the ones that you have to worry about the most. And learning rates are used for by the optimizers of both the generator and the discriminator. So you have to take into consideration to not use one too big or too small. Uh, you know why, but it gets even more trickier when you have to concern about that for two networks, let's say. But as I was saying, it is not possible to hyperpermitted tuning. It is possible, but you have to take in consideration that is not as you are used to, for example, of using an accuracy or just an F1 score or even a correlation coefficient when you kind of are building a machine learning model. So usually you hyperperimeter tune for those. You use, I don't know, different folds, you validate in the different folds, you do a gradient search, and you are okay and you select the best one. The one with the highest F1 score, or depending on the objective function that you define for your business. It's not the case for synthetic data generation. So what does mean to have the good score? That means that your synthetic data generation is good. So that is a question that is open because it depends on the downstream application on how are you going to use your synthetic data. So if you are going to use your synthetic data for machine learning purposes, meaning you are going to replace your original data with synthetic data, then that means that probably you should be building a machine learning model on top of the real one and on top of the synthetic data, and optimize towards a score which we call trained synthetic test real that is optimal. This is highly time consuming, but it's one way. Or you can use, for example, a fidelity score like it's used for images, which is the FID, that in a nutshell measures how similar the distributions between the real and the synthetic one are. But if you are looking to optimize privacy, what are the other metrics that you can consider? So, as you can see, it really depends a lot, and that's why the optimization or the design of the optimization ends up not being just a single metric usually, and you have to set different metrics, and that's why it's so useful to have the synthetic data generation as a pipeline of data, because you have to really experiment and to test and to version the tests and validations until you achieve the right result. Using YData synthetic, you have different architectures available, from the conditional WGAN to WGAN to the original GAN that we can see here. You can tweak the parameters as I mentioned. You can also trick the discriminator or the critique, as we call it, to train more times than the generator, just to compensate the fact that the generator usually converges faster. And then you can just train the synthesizer with your data, your conditional variable, your train arguments, and the definition of your numerical and categorical variables. Inside of YData synthetic, we will apply automatically encodings for numerical and categorical. But bear in mind, for different data types, such as date time, you would probably have to encode it previously of feeding to YData synthetic. Also, if there are other behaviors like missingness, you have to prepare them before. So my advice is always to go to pandas profiling, check the problems that might exist, check the warnings, prepare the data set in order to clean some of those warnings. Bear in mind, outliers, it's not a preparation that you should do. Your synthetic data should be as close to the real one, so keep the outliers. But all of the others like missingness and so on have to be prepared or pre-processed prior feeding into YData synthetic. And after training the model, which in this case, I for the purpose of the demo, I only trained 5 epochs, but 5 epochs, it's really a small number. Take that in consideration. So always go for a number at least of the 500 for the cardiovascular disease data set. I'll just feed my conditional array and I'll just sample the data. So it's very straightforward. It's just a couple of 4 or 5 lines of code and you are ready to go with your synthetic data generation. I've saved the file as a CSV, so I can use now in the third and last step of our process. So this also represents one-way flow, but this flow can be, especially around the second and the third step, should be repeated until you achieve the quality of the synthetic data that you are expecting. So again, I'm going to read both the real and the synthetic data. Let me just show you the real and the synthetic. And well, as you can see, with the exception of the index which I kept here, you can see that I generated both age, gender, height, weight, API, all the columns are here. Of course, you can tell a slight difference in terms of, for example, between the original and the real, which goes for the decimal houses, so the decimals at the weight variable, so you can tell here which is synthetic. You also can easily tell that it hasn't converged. So it only trained for 5 epochs, so it's normal that it hasn't converged, but you can easily tell that by seeing here a negative value at the level of the weight, for instance. But we also can check whether the original data had negative values at the level of the weight, which it didn't, if I'm not mistaken. So no, the minimum was 11, so definitely it did not converge. So now I can generate a profile report out of my synthetic data, just because similarly, it's a very easy way to compare the results between the real and synthetic data is having the profiles side by side. And bear in mind, in the next release of pandas profiling, we will have the comparison report automatically done. So you don't need to generate 2 separate reports. You can just generate one with the comparisons. And let me see if I can show you the reports specifically. Oh, file to file. Okay, so it's just building the profile. I'll be showing you in a couple of minutes. In the meantime, I'm just explaining the last step prior showing you. So do you recall the expectations I've generated right at the beginning on using the initial profiling here at the step? Well, this is where now this suit of expectation will become handy. So I'll be running my expectations against the synthetic data I've generated in order to check whether the fidelity remains at the level of synthetic data. Bear in mind, our target should be around the 90% if we are considering very good fidelity. But also bear in mind that between privacy, fidelity, and utility, there is always a trade-off. So if you want your data to be more private, you will lose fidelity and utility. If you want really close-looking data with high utility, yes, then target for the 90% when assessing, for example, the expectations. Okay. So I do have here my synthetic profile. As you can see, so the age when compared to the real data has a kind of a different distribution. So you right away can tell it didn't converge. So it totally generated a distribution that resembles like a normal one, which is expected because the noise does follow a normal distribution. So then we have the gender. Surprisingly, here we also can see that it did not converge yet because we see more imbalancement when compared to the real data, and so on and so forth. So this is a good initial exploration just for you to get a grasp on the quality of the synthetic data. Now, if you want to automate these validations without you having to see the side by side and going variable by variable, this is where the expectation suit kind of gets so interesting and so useful. I promise I'm just wrapping up. This is the last step. And yes, so here my expectations report. It sounds like we have 85.29% of success in terms of the expectations that I run on top of the synthetic data. Some of them failed. So all the required fields are there. We don't have any null values or missing data, which is nice. So we have, let me see, one variable that has failed. For instance, the API low have 6,000 unexpected values were found. So here you can see that values must be equal to 60 and less than 240. And we have values that are under 60, for example. We can easily check some of the examples here. So it's very useful for you to right away understand whether your data is remotely close to your synthetic and whether it makes sense, especially if it's a business kind of validation. You can only go between 0 to 100% because this is a percentage kind of field. This is the type of validations that we want to be sure they comply with. Otherwise, your synthetic data will automatically be spotted as fake. So yeah, I think that wraps it up. So
quick question from the amazing audience. Zan is asking, let's say I have customer data in the EU. When I create synthetic data, Great Expectations would make sure that I don't get any countries outside of the EU.
If you define that as an expectation in your suite of expectations, yes, totally. In this case, if your categorical is already in between some variables, so some values, indeed. But that also will your synthetic data generator probably provide you, because you can assume the country will be a categorical. And your synthetic data generation won't generate records outside of those values. That's probably that will probably happen. But what you don't want to generate is, let's say you are selecting the country as Portugal, and then all of a sudden Paris is the city associated with Portugal. That's probably the type of validation or suite of expectations that we want to make sure they comply, because the synthetic data generation might fail to understand that hierarchical or nested relation.
Perfect. All right. So I think the last thing before we jump is probably like giving a shout out to YData. Thank you for doing this. And Fabiana, thank you for showing us around. If anyone wants to learn more about what y'all are doing, I think it's just ydata.ai, right? It's easy as that.
Yeah. And especially if you want to talk about the open sources like YData Synthetic and Pandas profiling, which are supported by YData, data-centric AI community is probably the best place, or even at MLOps community. We are around, so just drop us a message. Any of those Slacks will do.